Hi there, this is a video on the Beltrami workbench in FreeCAD. I am Michel Sabourin and you are on the SimTube channel dedicated to hydraulic turbines. This video is part of a series on the Beltrami workbench in FreeCAD. Beltrami is a tool to design any type of turbo machine blade. It can be turbine, pump, fan, propellers, etc. All of them have the same topology and the same mathematical representation. Here we have a Francis turbine blade for the runner. We have also here the blade for the distributor. It's a wicket gate. And we can see the assembly of both here. Another type of geometry that is quite frequent, it's the Kaplan blade. Here we have the complete runner assembly. And here we have a blade for a pump and the complete assembly of the pump. So Beltrami can do any type of geometry for turbo machine. It works on the principle of modifying an existing profile. We can start from an existing geometry, or we can use the original profile that is embedded in Beltrami software. Let's start from scratch. I activate Beltrami, and Beltrami has two buttons. The first one is to start a profile from scratch, a cold start, and the second one is to modify the profile. Let's start, and this is the profile that is embedded in Beltrami. The information is classified in various groups. The first one is the user interface, and the last one is the 3D result. All the other are a kind of virtual plane that are used for mathematical calculations. Let's take a look to the user interface. There is three entities there. The first one, parameter, is a feature Python that is used to structure the data. The first parameter here is cascade rotation, so it indicates if the blade is rotating or not. The second one is the number of blades in the runner. It's only for documentation. And fillet is the number of curves. If I reduce to 3, immediately that there is one there, one in the middle, and one at the end. If we go to 9, it increases the definition of the blade in the transverse direction. Here is the number of points defining each curve. Presently there is 9 points. If we increase to 19, to 129, it influences mostly the leading edge shape, and in fact it should be increased for fabrication, for calculation for finite element or CFD, but during the work on the geometry definition it's not necessary to have it so high, so we keep it at 9 to maintain the reactivity of the software. And here we have the sense of rotation, so this is the positive, which is counterclockwise. If we put it negative, we have the clockwise rotation of the blade. The other interesting entity here is the sketch meridian. If we go in the sketch, there is 12 points defining the contour of the blade, and these points can be modified to suit your requirement for your design. So in that plane, here we have the leading edge and there is the trailing edge, and the flow goes from the leading to the trailing edge. If we do a modification, so we can move it, we can pull down a single point, we can displace any of the point here. Before closing, I will switch to constraint to lock all the position. And when I close the sketch, automatically the contour of the blade in the meridian plane is corrected and the 3D geometry is obtained accordingly. The spreadsheet Tableau Pilote is used to define the shape of the blade in 3D. In green, it's for the shape of the web, and in blue, it's for the thickness law that is built over the web to obtain the pressure and suction side of the blade. Let's display only the web. The first data, theta, define position of the leading edge and of the trailing edge. So for the leading edge, the position in degree is from 0 to -4. from 0 degree, you see, to -4 here on the top. And there is 4 poles that model mathematically the value. If, for example, we wish to lean the blade on the other side, we can just change the sign here of the variable. We can see the effect by using the update button here. And we obtain the result immediately. If, for example, we wish to have the trailing edge on meridian plane, let's see, presently it's from 30 degree to 60 degree here, from 30 to 60. Wish to put at 40. And again, I update the profile, and we have now the trailing edge on the meridian plane. Alpha are the angle at inlet and at outlet angle of the blade. So presently, the angle is -50 degrees around for the inlet. So it goes in that direction there. If we wish, for example, to have a 0 degree inlet angle, we can put 0 there. And we have a 0 degree inlet angle for the web. Of course, all the other surfaces follow automatically. As the alpha angle influences the energy transfer between the fluid and the blade, it is interesting to take a look how this angle evolved from inlet to outlet. And this is found in the virtual plane Planck cascade. Here we have, for each fillet from 1 to 6, the evolution of the angle. Let's look at the first one. So we see the angle is 56 degree at outlet and 0 degree at inlet. We see also that there is a little inflection here in evolution of angle. It could be desirable to remove this inflection or to correct it slightly by decreasing the length of the blade. This can be performed by reducing at the bend your angular position. If we put -30, we can see the effect here. We shorten the blade at the bend. And if we come back to the cascade, so the cascade is more regular and more interesting from a fluid analysis point of view. Now let's take a look how these pressure and suction side are built. There is 5 points defining the thickness law that is used. The variation of thickness are defined in the group plan épaisseur. There we can find 6 sketches corresponding to the 6 fillets. For this Francis profile, all the 6 fillets have the same thickness law. Let's take a look to the sketch for suction side at the bend. The leading edge is at the left and the trailing edge is on the right side. On top we have the suction side. It's not in the sketch, but we see the pressure side of the other fillet. The virtual length of the profile there is 1000. There is 5 poles that control the curve. The first one here, the second, the third, and the fourth and the fifth are at trailing edge for this type of profile. The position of these 5 poles are defined here in the spreadsheet. So there is the 5 poles, EX for the suction side, and IN is for pressure side. The 5 points and the X coordinate and the Y coordinate of this pole. All these values are scaled to fit the 3D length of fillets. Pole 1 is on vertical axis here. That way it ensures the continuity of tangency between the suction side and the pressure side. Pole 2 influences the thickness as well as pole 1. Pole 3 is on the x-axis to make sure to have an horizontal tangency at trailing edge. Pole 4 and 5 are at trailing edge. If we keep the full length of the virtual profile here, we will have a 0 thickness at trailing edge. This is why we have another variable, a pilast for suction and pressure side, that is used to truncate the profile during the discretization process. We can observe that here. These are the points that are retained to define the thickness law, and these points define the length. So this is the last point and the true trailing edge here. So this trailing edge will have a non-zero thickness. If we display the 3D result with the web, if we want to increase the thickness at the crown, So the thickness at the crown, the maximum, will be defined at the pole 2 on Y definition, and presently it's 50. If I put 100 and launch the calculation, we see that everything on pressure side remain constant, but we see that the profile has been modified on the suction side at crown, but not at bend. This kind of evolution from the bend to the crown is calculated in the pilot group, where we can find the variable we have modified, which is APAX2Y. APAX2Y, it's here. And if we look at the sketch there, we see that we have 100 mm for the point at crown and 50, and in between the curve that is used to define the thickness for each of the fillet from the bend to the crown is there. You have to realize that all these virtual planes give a good documentation of what is happening in the profile, but they must not be used to modify the profile. The modification of the profile must be done always from the spreadsheet. Before to end on this profile, just a few words on the results in group Domain 3D. The raw result of Beltrami method is contained in group points. Here we have the points for the web, here is for the suction side, and the point for the pressure side. Also we have here pressure and suction side assembly. So these points are exactly the same than the other, but they are in a single series. Following this series of points, we have curves for the web, for the suction side, for the pressure side, and also here we have the assembly of suction and pressure side. Then from these curves, we make some interpolation to create the surface. So we have the web, the suction side, the pressure side, and the complete surface of the blade. In the process, the tangency conditions of the complete blade surface is transferred to the pressure and the suction side. Just to complete the demonstration, I will increase the number of points and we will see that the discrepancy here will decrease. So 19 points, 129 points. At 121 points, there is a perfect fit of all the surfaces. Now let's go to the final example, the radial cascade that demonstrates the powerful capabilities of FreeCAD in parameterization. Here we have a Gadvain profile. This profile presents a simple contour in the meridian plane. It's a rectangle. Here in the spreadsheet, the rectangle position and size can be controlled, adding some simple instructions. The yellow background indicates the variables that can be modified. Here is the radial length of the profile. Here it's the distributor height. And finally, we have the outlet radius. This is the radius there. If we increase the radial length to 200, immediately the profile is modified, but the rest of the spreadsheet is not updated. We need to do the profile update here to obtain the value updated for the rest of the spreadsheet. If we look at the alpha variables, we see that we wish to have the same angle at inlet and at outlet. Moreover, it will be desirable to have a constant angle value between inlet and outlet. Let's see what we have presently. So we go in virtual plane Plan Cascade and we open the sketch. We have the two angles at inlet and outlet, but in between it's a curve. It's not a perfect line. It will be desirable to correct that. We have to modify the length of the profile, so we have to increase this value here. Moving this point up, we will have a straight line at some point. The spreadsheet suggests a value to adjust the theta outlet to obtain a straight line. I use this value and launch calculation. So it moves slightly a bit the outlet. It suggests to increase the value to 1282. You understand that we are in an iterative process and we have to iterate until we are satisfied with precision. So finally, we converge to this value. So both values here are the same. Let's see now at the sketch, and you see that there is no variation in the angle from inlet to outlet. We can observe that the shape of the web is not a straight line. This demonstrates that the spreadsheet expands significantly the parameterization possibilities in FreeCAD. On the website simtube.com, you will find a lot of information on this method. All the references that I will give are included below in the description. First, there is the SimTube YouTube channel, in which you will find a playlist on Beltrami. Then there is theoretical information on hydraulic turbine there, but for methods and tools, it's here, and you will find realization of the hydraulic profile of 3D turbomachinery blades. There is some theoretical aspect, so it's the analytic formulation of the method. There is also the numerical formulation of the method. And finally, you will have the user manual that you can access here. And in the user manual, you will find that modification of the hydraulic profile. You will find all the information on the way to modify the blade here through the user interface. So there is the three entities that can be modified: paramètres, tableau pilote, and the sketch meridian. Inside paramètres, if you click on it, you have the picture of the screen, and you can access each of the points here identified. So that way you have a good description of all the variables. For tableau pilote, it is the same. And the complete description is given here, and it is fairly complete. So this is the end of my presentation. Do not hesitate to contact me if you have any questions or comments. Thank you very much.